this lecture, we'll cover this fourth intermolecular attraction that will be covered in this chapter, what's called the ion dipole attraction. So if we take a compound like sodium chloride, so in the solid state, it looks something like this. It crystallizes into a cubic structure, where at each of these points you have a sodium or a chloride anion or a sodium cation. And of course, it's going to have sodium cations next to chloride anions so that you have positives next to negatives. Okay, so if we take that and add it to water, does it dissolve? Sodium chloride is basically table salt, and you know that table salt dissolves in water. So what does it look like when you dissolve it in water? It's an ionic compound. Right, so it's really Na plus and Cl minus in the solid state and in solution as well. So when in water, it ionizes. That means the cations are separated from the anions. So you'd have sodium cations floating around, and you would have Cl minus anions floating around separate from each other. Okay, so so we have water molecules. How's the sodium cation going to interact with water molecules? So what part of the water molecule would sodium interact with? Well, so for water, oxygen's partial negative, hydrogens are partial positive. So since sodium is positive, it would want to interact with the oxygen that's negative. So what's going to happen is water molecules will orientate themselves so that the oxygen atom is pointing towards the sodium cation. That way, that places the partial negative next to the positive of the ion. And of course, water has a dipole moment, right? Its dipole moment looks like this. It's in that direction. So this partial negative oxygen interacting with the positive charged cation is what's called an ion dipole attraction. So why is it called an ion dipole attraction? Because sodium is an ion, and water's dipole moment points towards the ion, because by doing so, that places the partial negative atom towards the positive charged cation. Okay, and how about the chloride? So how would it interact with water? Well, since Cl is negative, it's going to interact with the partial positive hydrogens of water molecules. So each of these lone pair electrons could be interacting with a hydrogen atom. And so what is that type of interaction called? Well, that's called a hydrogen bond, right? Why is it called a hydrogen bond? Because that's a partial positive hydrogen. That's part of the electrostatic attraction. So whenever you have a salt, an ionic compound, you always have a cation, you always have an anion. The anions will be hydrogen bonded to water, and the cations will have an ion dipole attraction to water. So if we took something like, let's say potassium carbonate, and if it dissolves in water, what would it look like? Well, so you would have potassium ions floating around in water, 2 of them for every 1 for every K2CO3 that dissolves. So each of the potassium ions would be surrounded by water molecules. Have an ion dipole attraction. So as long as you show one or two of these water molecules around the cation, that's fine. And then the carbonate, of course, you could draw a Lewis structure for it. Right, these two oxygens at the bottom may be negative, so that's, and the other oxygen's neutral and the carbon's neutral. Okay, so how is this going to interact with water? Well, again, so each of these oxygens would be hydrogen bonded to a water molecule. Because hydrogen's partial positive would be attracted to the oxygens that are negative. Of course, each lone pair could accept a hydrogen bond, but I would be fine if you just show one or two examples. Okay, so for the cation, it's usually surrounded by by 4 to 8 H2O molecules. So if we took an example like lithium versus cesium, so lithium would be more likely to be surrounded by 4 water molecules. Whereas something like cesium would be more likely to be surrounded by more water molecules. So why would cesium would it have more water molecules around it than lithium? They're both +1 charged, and the reason would be, so what do lithium and cesium have in common? They're both group 1 metals, and so as you go down the periodic table, size increases, right? So cesium plus is much bigger than lithium plus. So you can fit more water molecules around it. All right, so the bigger the cation is, the more water molecules you can fit around it. Okay, so lastly, let's take a molecule like glucose. So glucose looks like this. If you draw out the structure of it, so does that dissolve in water? So if you put that in water, so glucose is sugar. Does sugar dissolve in water? Yes. But it's got 6 carbons. So in previous lecture, we said if around 4 to 5 carbons. So we'll basically say it's not water soluble around 4 to 5 carbons. Maybe it's sparingly water soluble, but not very much. So we'll just say anything less than about 4 carbons water soluble. Greater than 4 carbons not water soluble unless something else is at play, which in this case, it could be branching. Once you branch the carbon chain, then it becomes more water soluble. Or in this case, right, you have 5 OHs. They can all hydrogen bond to water, and that can hydrogen bond to water as well. So if you put a glucose molecule in water, so let's just make sure you know how to interpret the structures. How many carbons is that? So that would be 1, 2, 3, 4, 5, 6 carbons, right? And this carbon has 1 hydrogen because it needs 4 bonds. This one has 1 hydrogen. That would have 1 hydrogen. That has 1. That has 1. That way each of those have 4 bonds, and then this carbon would have 2 hydrogens because it's got 2 bonds showing. That way each carbon has 4 bonds. So if you put glucose molecule in water, what does it look like? Well, each oxygen is partial negative. So each oxygen can hydrogen bond to a water molecule. Oops. Make sure you attach it to the hydrogen because the hydrogen is what's partial positive. And then each of the hydrogens on oxygen is partial positive, so each of those can hydrogen bond to a water molecule as well. And it doesn't matter if it's the same water molecule or different water molecule, most likely it's different water molecules. So as long as you showed a few of these interactions, that would be sufficient for me to illustrate the concept. Right, so each oxygen is hydrogen bond to H of a water molecule, and each of the partial positive hydrogens is hydrogen bonded to an oxygen of a water molecule. So this has nothing to do with ion dipole attraction. This is just another example of things being water soluble. So even though this has 6 carbons, it's water soluble because of all of the OHs. Okay. That's it for ion dipole attractions. So as long as you can sketch an example of the cations surrounded by water molecules with oxygens pointing towards the cations and the anions hydrogen bonded to water molecules through the negative atom or partial negative atoms, lone pairs, that's good enough.